Buongiorno, it's time for the third of our little lectures. So now that we've figured out the basic ideas of quantum mechanics, wave-particle duality, the relationship between wavelength and momentum, and then started to explore the Schrödinger equation and the idea that the curviness of a wave function tells us something about kinetic energy and also the requirements on the wave function, let's start our first little model problem. The first problem we're going to address is called the particle in a box. So that naturally begs the question, what's the particle? Well, a good model for this particle is an electron, one of our three heroes here. And it could be an electron in an atom, a semiconductor, maybe an atom in a molecule. The electron in conjugated molecules is an excellent example of a particle in a box that we'll use as a homework problem later. So there are really all sorts of models of things where electrons are confined that we find in real circumstances. For example, electrons in thin semiconductor layers might be one of the very best models. You can put down very thin layers, molecular layers, through a process called epitaxy and construct electronic devices that are known as quantum wells. There are things known as quantum well lasers, quantum cascade lasers that we use in our laboratory. And these things are all derived, or they all rely essentially on this model that we call the particle in a box. Okay, so there's the particle. The next question is, what's the box? Well, remember that that potential that we call V of x is the thing that is going to completely define every single problem we look at. So the box better have something to do with the potential because, well, that's the deal. And in better be a good hint there. We're talking about something that's imprisoned. It's totally confined to a certain space. So let's think about this graphically. We've got energy as a y coordinate here. We're going to have position x as the 0, and we'll put the x-axis on the 0 of energy there as normal. There's going to be some point 0, and why don't we make this the edge of a box? And what the box is going to be is something that the potential is going to go directly up to infinity, sharply up to infinity, an infinitely deep and high wall there. And then on the other side, at some distance we're going to call L, we're going to have another infinitely high wall. So there's the box, this space between 0 and L, where the potential is 0, that suddenly transforms to go up to infinity. So the characteristics are the potential is infinity for x less than 0, and then the potential is going to be 0, nothing at all, for this space where 0 less than or equal to x, less than or equal to L. And then outside of the box on the right-hand side, we go back up to infinity for x greater than L. So that defines this thing called a box. And think exactly of a prisoner confined between two very, very thick, strong, impenetrable walls there, and you've got your box. Now going to infinity, that kind of matters too, because remember that the kinetic energy in any system is equal to the total energy minus the potential energy. So if the potential energy goes to infinity, that means that the kinetic energy basically is going to be minus infinity for any finite value of total energy. So any value of energy we pick, we're going to have an infinitely negative kinetic energy. And that sounds pretty weird. So basically there's no way for this particle to be at all found. The probability is going to be absolutely 0 for the particle to be someplace where the potential goes to positive infinity. That's what we call a classically forbidden region. So this basic kinetic energy is energy minus potential. That's the classic definition of how things should be. And so if the energy is positive infinity, in classical physics, no way, no how can the object be there. And in general, any place where the kinetic energy is less than 0 is a place where classically an object is forbidden to be. Now that word classical should always be a warning to you that we're going to begin to tinker with this thing later. But for the potential being infinitely high, V equals infinity, that's going to turn out to be a completely sound restriction under any circumstances. You just can't be there. The particle is a complete prisoner to this space between 0 and L. Alright, so let's summarize this thing graphically. Let's get back to our box. So we've got our x-axis there. We've got a y-axis, which is always going to be energy, just about always in this class. There's the infinite wall of the potential at x equals 0, another infinite wall of the potential at x equals L. And then we're going to assume that there's some value of the total energy. So we're going to always draw that as a horizontal line because the total energy is a conserved quantity. It's not a function of x or anything else. The total energy that will be of that particle or of the total system when we get to more complicated problems. But right now it's just this one particle. The total energy is a constant number. So it's just going to be some value. And for the moment, we just pick a number. We assume that that horizontal line is the total energy of the system. All right, now we can draw the wave function. So there's again an x-axis. The wave function is going to have values in different places. Well, first of all, let's think about these classically forbidden regions, less than 0 and greater than L. Well, below 0, the potential is infinitely high. The kinetic energy would have to be infinitely negative for the particle to be there, so the particle's not there. We just established that. That means, remember, that by the Born interpretation of the wave function, if the particle isn't there, then the value of the wave function must be 0 in all that space. So that's what the value of the wave function has to be over there, below 0. And then if we go to the space greater than L, same thing applies. The potential is infinitely high, the particle can't be there, and so the wave function has got to be 0 over there too. All right, well that's beginning to set things up. The particle can't be in either region. The wave function has to be 0 for x less than 0 and x greater than L. So now we've begun to establish what the wave function has to look like in all the uninteresting parts of our little prison cell where we can't be anyway. But it's a start, and it's actually going to turn out to be a really important start. So now here's where it starts to get a little tricky. We've established the wave function has to be 0 outside of the box, less than 0, greater than L. But remember that we also said that the wave function has to be continuous. So we've got these two tricky points here at exactly x equals 0 and exactly x equals L. And also, remember that for the particle to exist, which we assume it is, it's in the box. It's not the particle that doesn't exist. It's a particle in a box. So in the box, the value of the wave function squared has to integrate up to 1 because that's the probability that you will find the object in the box. It's going to be a normalized wave function, and so when we take the wave function and square it, integrate from 0 to L, technically from minus infinity to plus infinity, but outside 0 and L, it's just 0, so we throw those away. So in that space, it's got to integrate up to 1. So now we have two interesting constraints here. The probability of finding the particle in the box is 1 because somewhere in the box it's got to be a particle in a box. So for that to be true, the wave function can't be 0 in the box. Everywhere in the box, at least. It has to have some finite value, so you can square it and integrate it up and get a number that is equal to 1. And that's it. Those are the constraints on the wave function. So now we've constrained the wave function. So let's go back to our drawing here. Here's the x-axis. Here's energy. And the y-axis. There's x equals 0 where the potential goes up to infinity. There's x equals L where the potential goes up to infinity. That's the potential there. And now another x-axis where we're going to draw the wave function. We already established that below 0 the wave function's got to be 0. Above L, above x equals L, the wave function's got to be 0. And now what we just got is that in between those points we have to go from 0 at x equals 0 to some value that isn't 0 for x inside the box, and then back to 0 when x is equal to L. Well, I got a pretty simple way of doing that. Let's go up and back down. That's about the simplest way I can accomplish that task, right? Just make a nice little curve that goes from 0 to some value and back to 0. And chances are it goes to the maximum value right about L equal 2 because this thing just looks sort of symmetrical. And if you know anything about physics, you know that physics loves symmetry. So let's think it looks something like that. So What this means is that the wave function psi of x must go from 0 at x equals 0 to a non-zero value, not 0, for x greater than 0, but it's got to get back to 0 when x is equal to L. Now, so far I figure this seems like sort of a big yawn, but it's about to get even more interesting. So here's our x-axis again. There's 0, there's L, and we now know the wave function, drawn in green here, has to go from 0 for x less than 0, not 0 x between 0 and L, and then 0 again for x greater than L. But that thing bending up away from 0 up to some maximum value and back down again, by gosh, that has curviness. There's curvature to it. It's got a non-zero value. It has to have curviness. Remember curviness from the Schrodinger equation. That is a big deal. So psi double prime of x divided by psi of x is less than 0. That has curviness, so this thing has kinetic energy. Remember, curviness gives you kinetic energy. The only solution to this problem with no kinetic energy that obeys the requirement that the wave function has to be continuous. Remember, that's forcing the function to 0 at x equals 0 and x equals L. And the only way for me to match that condition and have no curviness at all is just to make a dead flat line like this, psi equals 0 everywhere. But guess what? Psi equals 0 everywhere, we already said, that is a particle that doesn't exist. So the only way that the particle cannot be in the box is to annihilate itself and not be there at all. That's not a particle in the box. That doesn't exist. So for this problem, that is not a viable solution to the particle in the box problem. So forget about it. So this little video is a pretty short one because it's just fundamentally incredibly important, and it's super cool. It's totally quantum mechanical. And the idea is this notion of confinement. So we forced the particle into this space between 0 and L, and in quantum mechanics we call that confinement. We've confined the particle, so the wave function psi of x must go from 0, because 0 expresses that confinement, not being somewhere. It's got to go to not 0, and it's got to go back to 0. So by confining it, we make it go from 0 to not 0 and back. And the only way to do that is to have curviness, to have curvature, and a non-zero value of the wave function. The only way the consequence of the Schrodinger equation then is the thing has got to have kinetic energy. We call that 0-point energy because there is no way to satisfy the normalization criterion that means that the probability of finding the particle somewhere in this confined area has to be 1 and simultaneously satisfy the boundary condition requirement that the wave function be continuous and not wind up with some kinetic energy. So the very act of confining an object into some space is going to result in the wave function having curviness and consequently having kinetic energy. And the lowest energy solution we can possibly find is what we will call the 0-point energy. But it is never, ever, ever 0. And that's pretty cool. And that's an interesting, fundamental, absolutely important idea to end this short video with.